are already on D12 will be part of the second assignment, second test. Means that up to this lecture will be included on the first assignment, first test. Starting with this lecture, Zener diode, thyristors or control diodes, and the transistors will be part of the second assignment and second test. Now, first of all, I will take, a lecture today to present the Zener diode, or a special type of diode that is used in reverse biased. Now, if you are looking in this diagram, which shows the forward biased region and the reverse biased region, you notice that the forward biased region stays unchanged, means that the diagram reverse biased, you notice that once the diode is reaching the VBR, breakdown voltage or avalanche voltage, the diode, or this type of diode, may have a spike or increase in current for almost a steady voltage. This name, or this type of diode, was discovered in 1934. Initially, it was just the theoretical diode that was discovered by an American theoretical physicist, Clarence Zener. Bit later, Bell Labs took the idea, and they tried to make or build actually the diode. Basically, it's the regular diode that actually it's used in reverse bias. That's the type of diode, or only the type of diode that it's used in reverse bias. You notice that in reverse bias, the current, or the reverse current, it's almost constant as in the reverse bias region. Now you notice that again, I'm having a small increase in voltage up to a certain point. You notice that at this point, probably the diode, it will increase the current, from the minimum current, which is called the Zener minimum current, to the maximum current without changing, the voltage across the diode, which gives you an idea about, the applications that may be used when it's required to have a constant voltage for a wide or a large change in current. That current has to be between the two ranges, means that the two limitations that we have is the minimum current, the Zener minimum current, and the Zener maximum current. In terms of the symbol, you notice that I put, those two symbols, side by side. If a regular diode has, that symbol with an A and a K, a Zener diode has, those, twisted or, under a certain angle, the symbol on the cathode. In this way, we can differentiate the regular diode symbol with the Zener symbol. You may see another symbol which looks like, two triangles, put it, side by side, which looks like, this symbol. But probably you'll not see, too many Zener, symbols like this one, but just in case, if you are seeing, something like that, which actually it's, the same symbol that you may see it in probably most of the schematic diagrams. From where is coming that symbol? Again, if you're looking in this symbol, looks like a Z. And in this way, they try to make, the Zener diet, based on the name of this diet. Means that I'm having, two different regions or two different ways of applying the Zener diode. If the voltage is applied as a forward bias, or the positive on the anode and the negative on the cathode, the diode, it will act as a regular diode. Means that there is no difference between a regular diode and a Zener diode in forward bias. The only difference will be if the voltage applied across the diode is in reverse bias, or the positive on the cathode and the negative on the anode. Now, how it's made? It's based on, the same depletion region, except that those two semiconductors, the P and N semiconductors, are heavily doped, and in this way, you notice that the current is actually increased, between the two limits, the min and the max, due to a tunnel effect. It says, a tunnel effect because actually it will increase in the amount in the reverse current bias between the two limits, the minimum and the maximum. I mentioned that it used to operate in reverse breakdown region or voltage. The standardized values for those Zener diodes is anywhere between 1.2 volts and 100 volts. Roughly, that's most of the time, when we are seeing a Zener diode. Now, another application, or most of the application, it's used as a regulator. Now, the question is where it's required a regulator. And I make, an example again towards, to the capstone project. Suppose that I have, a 9 volt supplied voltage. We don't have to create another supply voltage, but one part of the circuit of the application that you are making requires just 3 volts or 6 volts or 5 volts. What we can do, we can actually add a Zener diode that it will lower the output voltage of the supplied voltage. Now, I mentioned that that's, the limitation. Means that we want to make sure that, the current that flows to the Zener diode, that's the IZT. T is for testing, and IZK is the minimum, and IZM is the maximum. Going back, to this diagram, you notice that the Z minimum and the Z maximum. Now, in order to avoid the confusion between the min and the max, to use, just a single subscript, they change, the IZ min as the IZK. From where is coming that K? From the knee value. Means that once, the voltage, it's almost in the Zener region or the breakdown region, the minimum current is reached. Means that the Zener, it's acting as a stabilizer or as a voltage regulator. Means that we are not using Z min, we are using, the IZK as the minimum voltage. Again, the question is how we can estimate, how we can calculate, the minimum voltage. Usually, I'm not saying always we can approximate, that's why I have, the approximation as the minimum current as 0.1 or 10% of the maximum current is not a rule, but as an idea about, the minimum value for the current and the maximum value for the current. Means that we have, a constraint, or we have, a condition in our calculations to maintain the IZT is the test current. Going back, to this diagram, the IZT is any currents or any value for the Z, the IZ or the Zener current that is between the IZ min and the IZ max. I will label, this current as the IZT or testing current. Now, on the characteristics, yes, I will show you a characteristic for a specific diode. I just download, the spec sheets for a diode, and I'm presenting, the specs and the most important characteristics that we have to take into account in our calculations. Vz is the Zener voltage, or the voltage across the diode that has to be maintained. Now, at this point, in this diagram or the previous diagram, Zener diode or the Zener voltage, I will take, as, the medium range or the mid range of the delta Z. Delta Z is the change in voltage as the current is increasing between the minimum current and the maximum current. Usually this change in voltage, or the voltage across the Zener diode when it is in the reverse bias, is very small. The value, or a practical value of the delta Z, can be in few tenths of millivolts or few hundreds of millivolts. If the Vz is a small value like 3, 5, 10 volts, probably delta Z will be in the range of excuse me, few tenths of volts. If the Vz is in terms of tenths of volts, you may see probably 100 millivolts as the Vz is changed. We'll make the assumption in our calculation that Vz is constant, or it's given in the data or in the specs in solving the problems. The IZT, I mentioned that it's the test current. You notice that I'll make, an assumption in a certain type of problem that IZT is the midpoint between the IZ max and the IZ min. Means that basically, the IZK is a very small value. I will take the maximum current and divide that maximum current by 2. And I'll make, the assumption that the IZT, or the test current, is between or half of the maximum current. What is the advantage of taking, the IZT, or simply IZ, half of the maximum current? Now, you notice that if I'm choosing, the IZT, or the test current, closer to the IZ min, means that I have a small swing, between the test current and the minimum current, and a large swing in increasing the current from the test current to the maximum current. The other way, suppose that I'm choosing the test current closer to the maximum current, means that a small swing in the test current and the IZ max, and a small swing between the test current and the IZK. I will show you one type of problem that is using the IZT, or simply the IZ, as the IZ max divided by 2. Zener impedance. Again, you will talk about, the static or dynamic impedance. Now, as the IZT is moving, between the two limits, the minimum and the maximum, the impedance actually of the zener is changing between the two limits. Again, suppose that the IZ or the VZ, or the supplied voltage or the voltage across the diode is constant, means that a change in current, it will change the impedance actually of the zener diode. I said that we are not using, the ZZ, the zener impedance or the zener diode impedance. We are using the IZK. Remember that? That's one of the characteristics or one of the values that we may use in calculation. K again comes, from the knee point, or the minimum current that is required to maintain a constant voltage across the diode when it's in reverse bias. Another useful quantity is the maximum current and the PD max. Actually, in diagrams, that's why I want to specify that we may see PD max, which has the same meaning with PD. That's the maximum dissipation power, the maximum power dissipated by a zener diode. That's the PD or the PD max. Again, has the same the same meaning or the same signification for the zener diode. We may see in the specs of a diode the IZ max, or the maximum current that can flow to the zener diode, that is not specified, but it specified the PD or the PD max. If the PD, the maximum power dissipation, is given, knowing the VZ, knowing the PD, we can find actually what is the maximum current flowing through the diode. Another specification that we are not using, but I want to give you an idea about the PD, or derated power, or derating factor. I mentioned that, usually those characteristics, or those, parameters of a diode, of a semiconductor, is given for a temperature that is 20 degrees. But what happens if the ambient temperature is greater than 20 degrees? Now we have to take into account, the DF, or derating factor. What that means that if the ambient temperature is greater than the standardized ambient temperature as 20 degrees, we have to lower actually the maximum power dissipation by a semiconductor, not just for the diodes, not just for semiconductors or for the transistors, in general speaking, for any semiconductors. And I make, a short example, basic example. Suppose that the derating factor is 0.67 milliwatts per degree Celsius. Means that we have to multiply that derating factor per degree with, the change in temperature. Suppose that the temperature is 40 degrees, the ambient temperature is 40 degrees. Means that we'll end up with the maximum power dissipation if the semiconductor, if the diode is working at 40 degrees, by a derating factor multiplied by the difference in the two temperatures, T2 minus T1. I'll take, 40 minus 20 multiplied by the derating factor. Means that I will end up with a PD max at 40 degrees less than the PD max at 20 degrees. TC, temperature coefficient, we may not use, the temperature coefficient in our calculations. The IS saturation or the leakage current, I mentioned that we measure that is in microamps or nanoamps, usually, in microamps. Nanoamps, it's, for very small semiconductors or the SSD surface or SMD surface mounted devices. Power dissipation, is the PZ or the PD, has the same meaning, is the VZ multiplied by IZ. Make sure that you understand the value of the IZ is, the maximum value, which gives you the PD or the PD max. If it is the testing value, it will be the IZT, means that the testing value or the power dissipation for a test value for the current is directly proportional with the test current. Now, VZ is constant, and we mentioned that that's, the application of the diode to maintain a constant output voltage or a constant voltage between the terminals of the Zener diode if the test current or the IZ is between the two limits, the minimum and the maximum current. In terms of the power, the Zener diode becomes in small power rating like 0.25. That's basically an SMD. The Zener diode that looks like the one that we did in lab, like 1N4005. That's a 0.5 or a 0.1 or 1 watt. The maximum power for a Zener diode is 50 watts. Means that we may not see lots of, Zener diode that are rated as 50 watts. In our examples, we'll take, probably anywhere between 1 to 10, 20 watts, probably no more than that. Because I'm trying, to stay closer to the real values. That's why we are not using, any large size or large power Zener diodes. I mentioned that usually we can determine or we can approximate the minimum current or the knee current or the IZK as 0.1 or 10% of the maximum current. Again, it's a theoretical approximation. This approximation gives you an idea about the minimum current and the maximum current. In our calculations, we are not taking, this approximation, but in designing the circuits, we may take, this approximation for a theoretical value. Ideal, the reverse breakdown has a constant voltage. I mentioned that VZ may be changed in a very small limit, like few tenths or few hundred of millivolts, but we are making, the approximation that, the VZ stays constant. That's why we are trying, to simplify our calculations. Now we have actually, based on, this circuit, if we are looking in this circuit, you notice that I'm having an input voltage, that's the VI or the Vin, the resistance that it will limit the current that flows through the Zener diode, and a load connected to the circuit. Now I may make, divide, this circuit in the three regions or the three sub-circuits. The input voltage or the supplied voltage, that's the voltage regulator, and that's, the load of the voltage regulator. You notice that the RL is connected between the two terminals, which is actually the voltage across the Zener diode. I mentioned that the Zener diode works in reverse bias, means that the positive of the voltage source is applied to the cathode, and the anode of the diode is supplied to, or it's connected to the negative of the voltage source. Now we may have, those, three operation region. You notice that if the V in, or the input voltage, is greater than the VZ, means that the Zener diode is on state, the voltage across the Zener diode is the VZ, and actually that's the voltage across the load resistance. Now you notice that the IZ has the IZ notation is the current that flows through the diode, the Zener diode, and the relationship between the IZ, the IR, and the IL. The current that flows through the resistance, or is supplied by the voltage source, stays constant. At this node, at this junction, the current is split in two currents, the IZ and the IL, or the IRL. Another useful equation that we may see in solving the problems is the PZ or the PD. Usually I'm using PD, is more intuitive, is the power dissipation of the Zener diode as the VZ multiplied by IZ. If the voltage is less than VZ, now I'm going back to the diagram of the diode, and I may go in this diagram or this diagram. Okay, now let's try to clean up, this diagram and make, those actually two regions on the reverse bias. Suppose that I'm choosing, the VZ. That's, the VZ. If the supplied voltage is on the left side, or is greater than the VZ, the Zener diode is on state, means that it will act as a Zener diode. It will regulate, or it will maintain a constant voltage as the output voltage for the circuit. If the Zener diode is less than the VZ, the diode is in off state. You notice that if the supplied voltage is between the VZ and 0, the diode is still in reverse bias, and the current through the diode, if it is in reverse bias with an input voltage less than the VZ, it will have a 0 current. Actually, it's a small current, but we are taking the approximation that, the current is equal to 0 if the input voltage is less than the VZ. In the forward bias region, I mentioned that the diode, it will act as a regular diode. Means that the only, let's say, condition for the diode to be in to work as a Zener diode or a voltage regulator is to have, the supplied voltage greater than the VZ, and this is the region, or this is the portion of the graph that it will be used the diode as a regulator. Now we end up with having, the V in greater or equal to VZ. Usually has to be greater than VZ, not equal, but theoretical approximation has to be at least the value of the VZ. And I put a note, and that's actually, one of the conditions that we have to make sure that the supplied voltage usually has to be greater than the VZ. That's why I put, always, be greater than the VZ. The purpose of the resistance are, again, it's used, to limit the current that flows through the current, what is supplied to the diode and is supplied to the resistance. I'm using the IL and the VRL. V in is the input voltage, resistance R, and the total current, which gives you an idea about, the equations or, the useful applications of this circuit. Based on this circuit, we may have three different types of problems. Means that one of the problem is the min and the max voltage that can be applied to a circuit that has a certain resistance and a certain Zener diode. The other problem is finding the value of the resistance R, knowing the V in, knowing the Zener diode, knowing the RL, and the third type of problem is for a given input voltage, a given resistance, a given Zener diode, to find the limit of the RL. Means that you notice that in this diagram, that's why I choose, this diagram shows you the a variable load resistance. Means that we have to determine what is the minimum and the maximum value of the load resistance, which is the RL. In terminal, what the diode does, again, I said that it's a variable impedance. That impedance actually reflects in the changing current. Again, applying, the KCL, because those two rules are applied in this equation. There is nothing to be memorized. It's just a notation. I will apply the KVL in this loop and the KCL in this node. Means that for a given current, for a constant IT, the IZ taking on the excess of the load current. Means that if the load resistance is decreasing, means that the IL is increasing, the IZ is decreasing, maintaining the same IT. If the RL is increasing in value, means that the IL is decreasing. If the IL is decreasing, the IZ, it will take, the excess of the IL current. Means that the IZ has to be maintained between the two values. Means that the IZ mean or the IZK and the IZ max has to be taken into account. Keep in mind that the IT always stays constant. The IZ, it will change between the two limits based on the value of the load resistance. Remember that those two branches are connected in parallel. The voltage is the same, means that the voltage across the RL is the same with the voltage across the Zener diode. In this way, we are maintaining a constant voltage across the load resistance or the load of the circuit, maintaining the voltage as positive on the top, negative on the bottom, but the current is variable, which depends on the load resistance, and the Zener diode, actually, it will compensate the change in the load in current, knowing that the IT has to stay or it's a constant current. Now, we'll take, the analysis, and we'll take, a next lecture, and I'll go through step by step those three different types of problems that may occur, from a practical point of view. The first type of problem is described in, this diagram. Suppose that we want to determine what is the range of the input voltage for a given resistance, for a given Zener diode. Now, I will make a short, and I will show you, a bit later, probably at the end of this course, the specs or the parameters of, a diode which looks like a Zener diode like this one. This Zener diode has a VZ as 10 volts, means that the constant voltage is maintained on the load or on the resistance that may be connected between the two terminals or across the Zener diode. And we have to determine what is the minimum and the maximum voltage that can be applied to this voltage regulation or the voltage regulator in order to have, a constant voltage as 10 volts in this example. The other problem is, or the other type of problem is for a constant input voltage, for a given VZ, for a given load. Let's try to determine what is the value of the resistance that has to be connected in series with the Zener diode to maintain the current and the constant voltage to a load that is connected to a circuit. And the third type of problem is to determine the limits or the RL min and the RL max. Means that for a given voltage, for a given resistance, for a given VZ, we have to determine what is the limit of the load resistance, the RL min and the RL max. To make just a short example, I said that for a given value, give me the data sheet. Now it's the data sheet that may be used, which looks like this one. That's the data sheet for a group of Zener diode. That's pretty one of the biggest companies in the world for semiconductors, fail charge semiconductors. They give the specs for a range of diodes, which is 4720, and what the difference between 28 and 58 is, the voltage across the diode. You notice that it gives you the size of the diode and gives the basic. I said that the PD or the PD max has the same meaning, and that's a practical application when the PD or the PD max has the same meaning. I said that is provided by the vendors as the PD or the PD max. The value is 1 watt. You notice that the size of these diodes are very small and they are rated as 1 watt. Maximum is 50 watts. You notice that, and I mentioned derated above 50. That's a practical value. That's specific for this type of diodes. It's provided by the manufacturer. That's why I made an example based on a practical value. Means that we have to derate, to decrease this value 1 watt based on the temperature or the working temperature on those semiconductors. And it's 6.67 milliwatts per degree Celsius. Means that above, this value, for example, 50 degrees means 60, 70, 80 degrees, the maximum power dissipation is decreased due to the derated value. The difference between 4728 and 4730, for example, those are the typical values. I said that the typical values are standardized values, means that the Zener diode becomes as 3.3, 3.6, 3.9, 4.3, 4.7, and so on. Those typical values are actually standardized values, but you notice that the delta Z, or the minimum and the maximum voltage across the Zener diode, is 3.135 and 3.465. That's the delta Z. In our calculations, we'll take, the typical value, means that we are not taking account the change or the variation of the VZ, means that we are using just the VZ value, not the delta VZ. And those are, the test current. They give you, some basic information about, the test current or the VZ. The VZ or the, for a given VZ, there's the IZT, or simply the IZ is like, 76. Those are given values. They are measuring and they are providing those parameters for a given test current. You notice that the IZK is given and is provided, and I'm using this value as 1 milliamp as the IZK, IZ max as 1.38 amps. You may see in milliamps, stay on the same scale as milliamps for the IZT or the IZK and the IZ max. As the second or the last two digits are increasing, you notice that the voltage or the VZ are increasing too. Means that 4747, for example, has the VZ or the typical value as 20 volts. Can be 19 or 21. That's the delta Z. Again, we are not using any change in these values. It gives you the logo, or how it's made. It's the F. You notice that again is the cathode always marked with a stripe or a band. Usually it's dark on the red background, on the yellow background, as I mentioned in those labs when I show it to you, different diodes. I took 4740, for example. I said that the IZK, for example, is 0.25 milliamps. The PD or PD max is 1 watt. We are looking to find what is the V in mean, or the change in between the two limits of the V in and the V max. For the or in order to find those two limits, we have to determine what is the maximum current. And you notice that the maximum current is not provided, but is given. The PD or the PD max, and knowing the VZ as 10 volts, we can determine what is actually the maximum current, knowing the maximum power dissipation, which is 100 milliamps. Once we know the maximum current, we are multiplying the maximum current with the value of the resistance, means that we can determine the maximum voltage and the minimum voltage. For the maximum current and the minimum current that flows through the resistance are that is connected in series with the Zener diode, we are taking the minimum current multiplied by the given resistance R, which gives you 55 millivolts. Now, I mentioned that we are applying KVL in this loop, means that the V in is the voltage VR plus the VZ, knowing the VR, which is imposed by the two limits of the Zener curve, we can determine the minimum and the maximum voltage that can be applied to this circuit. Means that using the minimum current or the IZK 0.25, the resistance is given as 220, gives you a small amount of voltage, 55 millivolts. 55 millivolts plus the VZ gives you the minimum input voltage that can be applied to the circuit in order to get a constant output voltage as 10 volts. To calculate the maximum current, to calculate the maximum voltage, the maximum input voltage, we are using the maximum current and the same resistance. Means that we are determining the voltage across the resistance R or the VR max using the maximum current that can flow through the Zener diode and the resistance R, which gives you a voltage of 22 volts. Adding the voltage or the maximum voltage across the resistance as 22 volts and the Zener diode makes the input voltage as a maximum of 32 volts that may be applied to the circuit. And that's actually, again, the circuit that always it's used in calculations. And I'm using, the same notation, V in IT. The current that flows through the resistance are the two currents, IZ, the IL. Now, in order to have, the voltage regulator, or how we can determine the min and the max value of the RL. Now, I'm applying the KVL. I mentioned that in the in this closed loop, and in top of that, I'm applying, the KCL in this node. You notice that the IT, which has to stay constant, is the sum of the two currents, the IZ and the IL. As the RL is increased, the other currents are changing, the IL is decreasing, and the IZ is increasing. To determine the minimum current, or the IL min, the IT minus the IZ max, and knowing the IZ or the IL minimum, we can determine the IL max. Reverse way, I'm decreasing the resistance, I'm increasing the current, means that the IZ is decreasing. Knowing that the IZ is decreasing, we have to determine what is the maximum load current. Knowing the IT and knowing the IZK, knowing the Z, the maximum load current, we can determine the minimum load resistance. Now, some basic applications, probably 1 minute or 2 minutes, I'll go over the regular schedule. We mentioned that we are using a voltage regulator. What has in it? Has, a Zener diode as the reference. As the input voltage or the output voltage is changed, sending, a signal to the error amplifier, which will control another semiconductor or the control element. This control element is actually a transistor, and next big unit is about the BJT or transistors. The three terminals, the input, which is terminal 1, the ground, terminal 2, and the V out, which is terminal 3. But I want to show you, the Zener diode, or the direct application of the Zener diode in integrated circuits. Another application that we may see is the Zener limited. Now, we can apply an AC voltage to a resistor connected in series with a Zener diode. Now, we have, the same approach. As the positive is applied on the top, you notice that the positive is applied on the top means that the cathode is connected to the positive, the anode is to the negative. Means that the diode, it will act in the reverse bias, means that it will limit the voltage across the diode to the VZ value. If or for the second half, or for the second uh, or the negative voltage applied to the diode. You notice that negative is applied to the cathode and positive is applied to the anode. Means that the diode, it will act as a regular diode, which will have a voltage across the diode in forward bias as 0.7 volts. Now, suppose that we are changing, we are reversing the terminals of a diode. I'm making the same approach, the positive on the top, negative on the bottom. Diode, it will act as the a Zener diode or a regular diode. Again, positive on the top, the positive is on the anode, and the negative on the cathode. The diode, it will act as a regular diode. If the negative is on the top and the positive is on the bottom, the diode, it will act as the Zener diode, which will limit the output voltage to the VZ value. Now we may have, the two diodes, back to back, means that the voltage is limited between the two rails is the VZ plus the 0.7. One of the diodes is in the reverse bias, the other diode is in forward bias. That's why I have, that plus 7 volts. The other application is combining actually a Zener diode with a regular diode. Now we are going into specific applications, but you may see this this application. For example, if I want to limit the output voltage to 6.3 volts. Now, again, from where it's coming, that 6.3, suppose that the VZ D1 and D2 are identical diodes. If the diode D1 is in Zener mode or reverse bias, the diode D2 is in forward bias. Means that I'm adding, the VZ plus the 0.7, which is the diode D2. And in reverse way, if the polarity is changed, the Zener D1 acts as forward bias, and diode D2 will be in reverse bias. That means the two limits, or the power rails or the voltage rails, it will be anywhere between the VZ plus the 0.7 and minus VZ minus the 0.7. Those are, specific applications, or, just the basic applications where we may use the Zener diode. Next lecture, we'll have the like in-class examples that maybe used for the assignments and the test too. I will see you tomorrow at 9:30, and make sure that I have, a piece of paper and something that you have to use, to write down, the examples that I will make as in-class examples. Sorry for the delay. I know I went, a bit over, but I'll make, some other lectures a bit shorter. Any questions, comments, concerns, please? Have a nice day, guys. Thank you.